Hello, I am going to be giving you some notes over section 2.4, relations and functions. Simply take some notes here, and then when you come to class tomorrow, we will go ahead and work on an assignment based on this. This is section 2.4 called relations and functions. If we're going to talk about relations, what we're talking about is any set of ordered pairs. So, just give you an example. Right here is a list of ordered pairs: 2, 5, 4, 8, negative 2, 0. That's a bunch of ordered pairs. That's the whole thing right there is called a relation. If you have a set of all of the first components, like the 2, the 4, the negative 2, that is what's called the domain of this relation. So the domain of this would simply be a list of those values. That would be 2, 4, and negative 2. The range, on the other hand, is all of the second components of that relation. So as far as the range is concerned, that would be those second numbers, which are 5, 8, and 0. Just give you a basic idea as far as what we're going to be dealing with when we talk about domain and range. A function itself is from a set of x to a set of y. In other words, you have two sets of values. Is a relation in which each element of x corresponds to one and only one element of y. And what this means is this. If you've got this relation right here, notice how we have the coordinate 3, 9, we have the order pair 4, 6, and negative 3, 6. Each of those x values are only used once. We've got 3 goes to 9, 4 goes to 6, negative 3 goes to 6. Each of these x values are only used once. Therefore, this right here, this relation right here, is considered to be a function. If we had maybe another coordinate out here where we had negative 3 and then maybe a different y value like 7, and that negative 3 actually was used twice, then that would not be a function. Here's a situation. If you look at this, it says this relation is a function. Here we got 4, 5, 4, 6, 1, 2, 10, negative 4. Well, notice how 4 is used with 5 as well as 6. Because of that right there, the x value is used for more than one y value, that is not a function. Okay? Now, we can also see if equations are functions. And again, what we're trying to figure out is for each x value that we can plug into this equation, is there only one y value? And it might be easier to figure this out if we can actually take this equation and solve that equation for y. And that's exactly what I'm going to do here. I'm going to subtract this 4x cubed from both sides. I'm going to get this y by itself. So I get negative 7y equals, I could just write this as 2 minus 4x cubed, and then divide through by negative 7. So I'd have that over negative 7. I can just express this as y equals, I'm going to express this as negative 2 sevenths plus 4 sevenths x cubed. Now, what we're trying to figure out is this a function? We're trying to figure out if this is a function. If for every x value we plug into this equation, you only get one y value, and only one y value, then it is a function. And if you think about that, if you substitute 0 in here for x, there's only one value that you get. That would actually be negative 2 sevenths. If you substitute negative 1 in here for x, and simplify all this, that's only giving you one answer. Therefore, for every x, sorry about that, for every x that we plug in there, you only get one value. So this is a function. If we look at this second equation, however, oops, getting fancy here. If we look at the second equation and do the same thing here as far as solve that equation for y, watch what happens. If I subtract that x squared from both sides, I get y squared equals negative x squared plus 16. Now, in order to solve this for y, I still need to take the square root of both sides. Well, when you take the square root of both sides, this is not quite the final answer. We still need one thing here, don't we? You betcha. And that is the plus or minus sign. When we take the square root of both sides, that becomes plus or minus the square root of negative x squared plus 16. So think about this. If you plug any value in here for x, if we plug 0 in here for x, we have 0 plus 16, which is 16. But then the answer is plus or minus the square root of 16. So not only do we get a positive number, but we also get a negative number. Therefore, for each x value we plug in, we would get two answers. We get more than one solution for that equation. Since we get more than one solution for each x value, that is not a function. That does not follow the definition of a function. Now let's get back to this idea of the domain. You've been taught probably before that the domain, simply put, is dealing with the x values, and the range is dealing with the y values. Well, we're going to focus on the domain only. And what I like to do here is think not necessarily of what are all the values that we can plug into this equation. The bigger question is, are there any values that you cannot plug into this equation? And if you look at this first one, we've got f of x equals 2x plus 5. Well, there's nothing that you cannot plug x into here. Or no, there's nothing you cannot, I'm sorry, there is no number that you could not plug in here to get a legit solution. You plug 0 in, a 1, a 2, a -7, a -6, anything you want to there, and we would get a legit answer. So the domain for this would simply be all real numbers. Now, what we've been doing here is we've been using interval notation. So let's do the same thing here. This is the interval from negative infinity to infinity. That would be all real numbers for this first function. However, here's an example, maybe a better example here, so you can see where the domain is actually restricted. What we've got with g of x is 1 over 4 minus x squared. Well, that's a fraction. The one thing you cannot have as a fraction is the 0, or the denominator, to be 0. So what we're going to do to figure out this domain is I'm going to set that denominator equal to 0, because the values for that equation would make the denominator 0, which we cannot have. So what I'm going to do is I'm going to just add that x to both sides to get 4 equals x squared. And like what we did on that last slide, when you take the square root of both sides, you would have x equals plus or minus 2. So our domain is restricted in a sense of x cannot equal 2 or -2. Alright, so we could say, one thing we could say is x cannot equal 2 and x cannot equal -2. We've got a restricted domain. If we want to use interval notation, then what we could do is simply say that the domain will be all the values from negative infinity to -2, non-inclusive, because x cannot equal -2, in union with another interval from -2 to 2. Okay, and then since x can't equal 2, that actually is going to be in union with the interval from 2 to infinity. Let me put it this way. If I were to draw a number line of all the values that is included in the domain, we said x cannot equal -2 and x cannot equal +2. What it can equal is absolutely anything else. So we have values on interval. We have 3 intervals here. There's one, and that's this one. Here's the other one, that's this one. And here's the third one, which is this. Moving down here with this last function, again, what we want to figure out here is what is anything that x cannot be. And if you notice, we actually have a radical sign within that function. Well, what can you not take the square root of? Exactly, a negative number. I mean, we can do that and get a non-real solution, but we want to figure out, hey, we want all the values that give us real solution. So what I'm going to do is set that x plus 4 to be greater than 0. Because whatever we plug in here for x has to give us a value that is not negative. We can't have a negative number in here. We also, if you notice, I said just greater than rather than greater than or equal to. We could take the square root of a 0, however, this is in the denominator of a fraction. So that's why I left this as greater than rather than greater than or equal to. Now in solving this, if I subtract that 4, I simply get x is greater than -4. And sometimes it helps just go ahead and use 0 just to kind of have that in there. Here's negative 4. What we're talking about is x can be any of these values off to the right of negative 4, giving us a domain of negative 4 to infinity. And just to give you an example here, if x was something over here, like negative 5, you would have negative 5 plus 4, which is negative 1. You cannot take the square root of negative 1. If x is negative 4, negative 4 plus 4 is 0. Well, you can take the square root of 0, that's 0. However, that would give us a 0 in the denominator. We cannot do that, that's not a good thing. Alright, so this would be our domain here. One final slide here for the evening, thanks for your patience, is the vertical line test. You may remember this from last year, so you might be turning this off by now. What the vertical line test was simply saying is, if you've got a graph, for example, if we have maybe a parabola, try to draw a parabola here. If you can draw a vertical line anywhere through that graph, and it only intersects that graph in one place, then it is indeed a function. So, if we draw a vertical line here, here, so wherever, and it only touches that graph in one place, then it is a function. Okay, another example, we could do some kind of a cubic function. Maybe you have a graph that looks like this. It's continuous there. Again, if you draw a vertical line anywhere through that graph, that is going to be a function. Some non-examples, or maybe just one non-example, if you have maybe a sideways parabola, or if you draw a vertical line here, it'll actually intersect that graph in more than one place. Therefore, that is not a function. Another example, something we've talked about before, is actually a circle. Okay, a circle is not, that's supposed to be a circle. That is not a function, obviously, because if you draw a vertical line here, well, that intersects that in more than one place. All right, thanks for all that you do, and we'll see you in class. Bye-bye.